This is section 11.1 on sequences. So the first example says list the first 5 terms of the sequence. So we can simply just start with 1 for n. If you plug in 1 for n, you're going to get a sub 1 is equal to negative 1 to the 1 times 1 all over 1 factorial plus 1. And if you evaluate that, you will get negative 1/2. For n equals 2, same thing. You should get 2/3. N equals 3. Should get negative 3/7. N equals 4. Should get 4 over 25. And the last one, should get negative 5 over 121. All right, the next example says find a formula for the general term a sub n of the sequence. So you want to notice that it is a geometric sequence, and what makes it a geometric sequence is that it has a common ratio of negative 1/4. That is, if you multiply the first term by negative 1/4, you'll get negative 1. If you multiply that by negative 1/4, you'll get the next term, and so on and so on. Because it's geometric, that means you can use the formula for the general term of a geometric sequence, which is a sub 1 times r to the n minus 1. So that's just the formula for a geometric sequence. And so we already know what the first term is. It's 4. And now we know what r is, and that is pretty much it. And that is our final answer. All right, for the next problem, they say determine whether the sequence converges or diverges. So the way you determine whether it converges or diverges is whenever you have a sequence, you just have to take the limit as n approaches infinity. And if the limit exists, it converges. If the limit does not exist, it diverges. So let's take the limit as n approaches infinity of the sequence. So whenever you have a limit like this, you always want to divide by the highest power of the denominator, which in this case is n to the 1. So if you do that, that means this is going to be the same thing as dividing everything by n. If you divide that by n, you're just going to get 5n. And if you divide n by n, you get 1. So as n approaches infinity, this term will go to 0, this term will go to 0, this term will go to infinity. So you're going to have infinity over 1, which is infinity, which means that this sequence diverges. All right, same thing for this example. So we start off by taking the limit as n approaches infinity of the sequence. And we want to divide each term by the highest power of the denominator, which is square root of n. So if you do that, you're going to get the limit as n approaches infinity of 3, 1 plus 2 over square root of n. So I divided everything by the square root of n, square root of n, square root of n. That's how I got this expression. And we know that this will approach 0 as n approaches infinity. So therefore, we get 3 over 1, which is 3, which means that the sequence converges. All right, let's move on to the next example. Actually, they start us off with a theorem. It says that if you have a sequence that's in this form, then it's going to converge if r is greater than -1 or less than or equal to 1. And it's going to be divergent for all other values of r. So here it is. If r is between -1 and 1, it's going to approach 0. If r is equal to 1, it's going to become 1. If r is any other value, then it just diverges. So let's look at this example. Most likely we're going to apply that theorem. It says determine whether it diverges or converges. So once again, we set up our limit. All right, in this case, we're going to divide by this term because it's in the denominator. So we'll divide by 9 to the n, the power. So that's going to become 4 to the nth over 9 to the nth, 1 over 9 to the nth, and if you divide this by 9 to the nth, it just becomes 1. We can rewrite these two terms as a fraction, 4/9 to the nth, because they both share the same exponent. And similarly, we can do the same thing to the 1/9 to the nth. And the reason I wanted to write it in that form is so that now we have it in this form where 4/9 is our r and 1/9 is our r. And so because 4/9 and 1/9 both are between 1 and -1, that means that the limit is going to approach 0 as n approaches infinity. So these are both going to go to 0 and 0 by this theorem here because r is 4/9 and 4/9 is between these two values. Similarly, 1/9 is also between these two values. Therefore, these are both going to go to 0 as n goes to infinity. And so we're going to have 0 over 1, which is just 0. Thus, this is going to converge. All right, and I believe there is one more problem. So let's look at that last one. All right, determine whether the sequence converges or diverges. So same thing. So let's take a look at this one. Let's start off by taking the limit as n approaches infinity of -1 to the n plus 1 times n all over n plus radical n. All right, so we use the same technique as we've been using. We divide by the highest power of the denominator. N has a higher exponent than square root of n, so we're going to divide everything by n. So if we do that, we're going to get limit n approaches infinity of -1 n plus 1. This is going to become 1 because we're going to divide by n, so that's just going to disappear. It's just 1. And this is going to become 1. And this is going to become the square root of n over n. Well, the square root of n divided by n, you can imagine n being written as square root of n times square root of n. So if you cancel one of them out, you're going to have 1 over square root of n. So that's what this becomes. This just becomes 1 over square root of n. After you divide this by n, it becomes that. All right, and we know as n approaches infinity, this term will approach 0. So we're going to have the limit as n approaches infinity. Well, let's think about this. If n is 1, this is going to be 1. If n is 2, it's going to be -1. If n is 3, it's going to be 1. If n is 4, it's going to be -1. So it's going to keep going back and forth for 1 to -1, 1 to -1. So it's going to take on those two values. Going to take on values of 1 and -1 indefinitely, which means that it will never converge. It's going to always be 1, -1, 1, -1, so on and so on forever. So therefore, it never converges. It's divergent. All right, and that is the end.